I think, yeah, computation is a powerful tool, but it can be even more powerful if we find ways, like through Compas, for example, right, to share our methods with others and to learn from others' methods and to connect things together. Low carbon, less waste is not enough. We need to do more. And what is more? We need to really design for circularity. Everything that we have done by breaking, changing, bending, interpreting the rules.
Welcome to PA Talks. In this episode, we are delighted to introduce Philippe Block, a distinguished professor at ETH Zurich and also co-director of Block Research Group. Philippe is a pioneer in applying computational methods to architectural and structural design, pushing the boundaries of both traditional and innovative materials. His notable projects such as Armadillo Vault and Nest Hilo Unit demonstrate his commitment to reducing environmental impacts by strengthening the geometry. Join us as we explore Philippe's journey through the intersection of engineering, architecture, and sustainability, where he harnesses technology not just as a tool, but as an integral part of architectural innovation and environmental responsibility. Before moving ahead, let's take a moment and spotlight Pacademy, an online architectural educational platform dedicated to the exploration of parametric design, computational tools, and artificial intelligence in architecture. Pacademy serves as a bridge to advanced design techniques, fostering collaboration with pioneering architects and designers. Through the online courses at the Pacademy, we dive deep into the multifaceted world of computational design, engaging with a wide array of topics that push the boundaries of architecture. You can register and join the live workshops or watch the previous studio workshops recordings. Don't forget to subscribe to our YouTube channel and hit the bell notification so you don't miss any new uploads. So if you guys are ready, let's get into the podcast. Well, hi Philippe, thank you so much for joining PA Talks. It's good to have you here.
Hi Hamid, well, thanks for the invitation. Yeah, very happy to be here indeed.
Thank you so much. So you're one of the pioneers of digital fabrication and also structural engineering. So I wanted to know a little bit about your background and your experience and how did you become interested in structural engineering and architecture?
All right. Well, I kind of rolled into this a little bit by accident. As a high school student, I did a lot of sports. I was very good at math. I loved math. I took all the most amount of hours that I could in math, and I also loved arts class. So those are maybe three things that kind of were important in my life. And so I actually wanted to do something that kind of combines these things. And so first I looked actually even to go to do engineering in the military, because then I could continue my sports career and doing a very difficult kind of study at the same time. But then it was my arts teacher that said, like, you can absolutely not go in this direction. You have so much creativity. It would be really a waste of your life if you would not do something with your creativity. So it's thanks to my arts teacher in high school that I looked at then other options, and I saw that you could do in Belgium. There is this degree where you combine engineering, structural engineering, and architecture. And I thought, well, that is maybe best of both worlds. I can really kind of continue my love for maths and kind of the engineering sciences, but at the same time not ignore my creativity. At least that is what my arts teacher kind of claimed. And then I got into it, and yes, indeed, this was the perfect mix for me. And then that's how it started. So actually a bit by chance. Of course, I could tell you a story that I played with Lego blocks and stuff like that, and that is why I wanted to be a builder. Not really.
Yeah, please go on, go on, because the name Block is also quite interesting.
That's right, yeah.
Hear this story.
Well, so I guess, in fact, funny that you mentioned this, because after my master thesis defense at MIT, my advisor, John Oxendorf, started indeed kind of his introduction by saying, well, I was really destined to work with masonry, to work with blocked architecture, and because it's of course in my name. So You're not the first one that makes that connection, and indeed it ends up being my career, working with blocks. Yeah.
Yeah, that's quite interesting. And can you also discuss a little bit about your joining to ETH Zurich and also the formation of Block Research Group? Maybe you can discuss a little bit about the inspirations, motivations, and how was the process?
Actually, there also, I kind of rolled into this a little bit by chance as well. I didn't even know ETH. I never visited Switzerland before. And so at the end of my PhD at MIT with John Oxendorf again, I already had a job lined up to become a structural designer with one of the biggest firms that we know. And so I was very excited to start to go into practice and do things and stuff like that. And then John shared this call for this professorship at ETH. And it was really as if they were describing me. Like really the call was like, oh my God, this is like a description of who I am. And then I thought, okay, let's apply, but what is this ETH? Then they explained to me that ETH is the MIT of Europe, or I would say MIT is the ETH of the US. That's what I would say now, right? As a slight provocation. But so I was intrigued. I applied, and then indeed I kind of stood out because I had a very different profile than the other people applying. And then I got the invitation to start at ETH. Well, in fact, they called John to make sure that I would indeed finish my PhD in time to come to ETH, because I was still a PhD student, still doing my PhD, and so they asked. So I had to then wrap up as fast as possible to start at ETH. So that's kind of how I ended up here.
So this is the process after your PhD. You finished the PhD and
No,
MIT.
I was still doing my PhD at MIT, so I got the job 9 months before I finished my PhD. So kind of
I mean yes.
Oh, I directly
correct.
came here after my PhD.
Yes.
Yes, that's right. And then how did we set up the group? Well, like you pointed out, with such a perfect fitting name somehow, I thought it was kind of appropriate to call it the Block Research Group, which obviously doesn't stand for my name, but for the fact that we do masonry.
Yes.
No, and so I set up the group, and I invited my best friend from Belgium, with whom I did my first master thesis at the VUB in Brussels, Tom van Mele. I invited him to join, and then the two of us have been developing and the group since. So it's in August, it will be already 15 years. So I've been here at ETH already 15 years. So wow. It's kind of crazy to think that I still have a 20+ year career ahead of me in academia. So we'll have to think what we want to do next. But so the BRG, so how did it all started? Well, my PhD at MIT was actually on the assessment of historic structures. So I developed a method to really understand the stability, to understand and visualize the stability of historic structures in masonry, so vaulted structures specifically. During my PhD, I kept being interested in design, and I already saw the potential of actually bringing back this lost knowledge, these kind of beautiful principles, why simple structures in stone can still stand after 400, 500 years. So I realized that we really forgot about this in modern design, both in architecture, like how to find these geometries, but also in engineering, how to safely engineer them. And so that was the starting point of the BRG. Can we actually start from the historical principles of equilibrium, of good structural form in compression, and can we actually bring them to modern design? That's how it started, but then on the computer you can generate whatever you want. So very quickly, we had to not only develop tools to discover these structural forms, but we also had to figure out how to make them. So then digital fabrication started to have to be another expertise that our group offered. Then at a certain point, you have these funky geometries, you have built them, but then how to bring them on site. And so we had to really learn how to optimize construction on site, the the logistics, the sequences of construction and so on. And then now we got quite bored and if not frustrated by doing pavilions and prototypes and so on. So we want to do real projects. And that means that we have to interface with real practice, with real collaborators and so on. So now we even have extended our expertise on developing computational tools. So our colleagues, for example, call our computational framework BIM on steroids. So that we have very effective ways to insert our innovations in real projects, right? So it started from exploration to, okay, now what? How do we build it? Then it moved into how do we scale it up and realize it really in practice. And now our expertise is actually on developing methods to really collaborate with practice. So that's kind of a bit the 50 years in a nutshell, maybe.
Wow, incredible. And you discussed about advanced fabrication tools and computational tools because you're using these cutting edge technologies in your process, whether it's design, whether it's the fabrication. How do you see these advancements is reshaping the future of architecture and engineering?
I mean, yeah. So you point out it's obvious that we use a lot of computation and that we use the best tools available for fabrication as well. I want to maybe before I can. I mean, so it's clear that is what allows us to innovate, right? So it's the only way. I mean, so there is computational methods, integrated computational approach in all aspects of our projects, but. I mean, first and foremost, though, the principles or the real engineering in the principles in the background need to make sense, but we use computation to be able to introduce non-standard geometry, so structural geometry, and to realize it efficiently, economically. To develop solutions to provide structural geometry at scale. So that is how we use computation, right? We also use computation to kind of start to challenge or combine or compromise between different criteria. I mean, all the typical things, right? But so I think obviously we use computation as a super effective tool, but perhaps more importantly, in fact, is that from the beginning, Tom van Mele, my partner in crime, has been developing a computational framework for the BRG. And the reason that we did this is because we noticed that each time we have a new researcher, each time that we have a new PhD student, we almost have to start over again. We lose so much knowledge each time when someone left. So we really set up a framework that we could robustly share or build up our knowledge over generations, right? And this in-house platform, so the BRG computational framework, became so powerful that then in the NCCR Digital Fabrication, so the national center that focuses on digital fabrication here at ETH, there was an interest to share it with everyone, right? And so, for example, Grammatio Kohler Research, but also Benjamin Dillenberger, and many of our colleagues here started to use this framework because they recognized that not only our PhDs could learn from past generations, but we could all learn from each other. And of course, what I'm describing is this framework is entirely open source. This framework is called now Compas. And so,
what do you mean by framework? Yeah. Maybe you can elaborate on that a little bit, because I see, is it like a software? Is it like a code? Is it like a workflow to follow?
It's actually all of the above, Hamid. It's really all of the above. It's the holy grail of computation, truly. So it is unlike, for example, Grasshopper or Dynamo or whatever you use. It's not software or even platform dependent. So it's fully agnostic. So it's Python based. It's very robust. It wraps almost all relevant for architectural geometry, all relevant computer science libraries and packages that are notoriously hard to translate and to implement in your architectural workflow. It makes connections to structural engineering software, to other things, and so on. It has as a core super lightweight and efficient data structures that actually allow you to do computation properly. So it's really based on literature. It's not kind of improvised like connecting wires in Grasshopper and so on. Yes, of course, you can mimic certain data structures, so this really implements all the state of the art and so on. So it is our attempt, and it's actually there. So Compas 2 is released. It's super robust, used now worldwide by many people, not only in academia, but also spin-offs are based on Compas. Companies are starting to use Compas and so on. We haven't made sufficient noise, by the way, because we wanted to really develop something that is very robust and makes sense. And only now, in the next couple of months, years, we will start making noise about it. But there is already many, many things. And in fact, every single project you know from us was developed by combining components of Compas. And so that also means that when you actually go to Compas, you can find all the techniques, all the tools that we use, right? So we share everything with everyone. And we do this because our industry needs to do better. We need to build better. Absolutely. With the climate, with the resource crisis, and so on and so on. And so we find it important that we all learn from each other instead of all in our own bubble, kind of trying to save the world by ourselves, right? So we're not going to get there.
It's open source and it's allowed to be added by other people on top of it as well?
There's an entire kind of, the credits always go to the owners of the new packages. It's entirely open source. It even has kind of things like cookie cutter kind of files, so that when you like how our documentation is generated, you can generate it automatically in the same style. If you like how a BRG tool works, then you can take the BRG template and directly release your code. But what's cool is that your code will work in Rhino, will work on the browser, will work in Blender, will work on a Raspberry Pi, so it works anywhere, right? And so we spent literally a decade, and when I say we, I say the royal we, because it's first Tom and now an entire community. So there is also a Compas association with many contributors. It's a fully open source project. So it's more than 10 years of work to wrap powerful libraries, to make connections robust so that you never have to figure this out. So for new researchers, this is perfect, right? You don't waste your time setting up your own data structure. You don't waste your time trying to figure out how to talk to this software, and so on. You get this for free because we thought, how stupid is it that so many people with brain power use brain power to waste multiple months to figure something out. And so that means that we witness now also in our building, not only in our own group, but when we collaborate with other groups that use Compas as a starting point, that literally you need maximum an afternoon to sit together, to tie your different pipelines together and to go forward. And so we use Compas also in practice. For example, when we do projects with the Shajeh Bhushan's group at Zaha Code, then Compas is there to unify the pipelines. And so, for example, maybe you've seen the Striatus project, this fully unreinforced concrete 3D printed bridge that we have done in Venice. And now the Phoenix Bridge is the permanent bridge that we built in Lyon. Yeah. All of this came together. So Zaha Code has their own computational pipeline. Incremental 3D has their own computational pipeline. The BRG has their pipeline, their computational setup, which is Compas. And then Compas kind of smoothly connected all of this together with no effort, right? So all these different things were integrated through Compas. Anyway, maybe we shouldn't talk about Compas only, but I do think it's important to mention this because I think, yeah, computation is a powerful tool, but it can be even more powerful if we find ways, like through Compas, for example, right, to share our methods with others and to learn from others' methods and to connect things together, right? And so that excites me. I think that's where we need to go. That's where we need to go. Open source, computational, that's the way to go.
Of course. Sounds great. Well, thank you so much for all these efforts, creating all these frameworks for the whole community. And going beyond the boundaries. You guys also emphasize on a lot about the strengthen through geometry and to address the climate challenges. Can you discuss a little bit about this? How does this help into the solving, climate and environmental issues?
Well, strength through geometry is actually central to what we do, because I talk now more about the methods and our ambitions to kind of to also bring rigor, computational rigor to our field and so on. But actually, to the core, we are a structural design chair. We are the chair for architecture and structures at ETH. The key thing that we try to demonstrate is indeed what you mentioned, strength through geometry. So what does that mean? That means that to get actually the right geometry, you can reduce the amount of material that you need because you place material where needed. So the geometry generates the strength or the stability instead of the high strength material, high tech materials and things like that. So what you get when you get the geometry right, and I'll give you an example. Of course, we are mainly known for our work in masonry. We use masonry for really masonry structures, for tile vaulted structures, for cut stone structures and so on and so on. But we also, one can consider concrete as an artificial stone, so a material happy in compression and not in tension. So also when we do concrete 3D printing or when we innovate in concrete, then we will also use strength through geometry. We will use the right geometry for a compression dominant material. So that means an arch or a 3D arch, a vault and things like that. So if you actually do this, if you place material where the natural flow of forces is in compression, then you can not only, I'll give the example of a floor plate. Then you can reduce the amount of concrete by 70%, wow. Right? And you reduce the amount of steel by 90% compared to a regular reinforced concrete floor plate. So that is how powerful it is to actually follow the natural flow of forces. But then on top of that, and that is something that we also celebrate and use, is that if you align your geometry to where naturally the forces are, then the stresses in the material are very low. So that means that you can use structurally low strength materials. And why this is important is because there's almost a one-to-one relationship between how strong a material is asked to be and how much it emits, so what's its carbon footprint is. And so that also means that strength through geometry, we not only use it in our high-tech projects where most of the people know us from, but we also use this in our projects in Africa. We work now with the government of South Africa to develop a super low-cost floor system that really uses cheap local materials actively. And we use strength through geometry to activate waste materials that have lower strength kind of properties. We use strength through geometry to really, and not in a naive way and thinking about kind of like pavilions and stuff like that, but to really investigate if we can use, for example, mycelium products as real structural materials, right? And so that's the beauty of strength through geometry, is that it allows to significantly reduce the material, at the same time activate lower strength materials in a safe way. So basically, strength through geometry is a new term that we coined perhaps to say the same principles why the beautiful Gothic cathedrals are still standing after 500 years. That is strength through geometry.
Yeah.
Actually, Hamid, can I add one more thing? Something that recently, because we are continuously learning, we are evolving, we're self-critical about all our projects, very much so. Lately, I'm convinced, and I am an extremely strong advocate, that actually low carbon, less waste is not enough. It's not enough. We need to do more. And what is more? We need to really design for circularity. We really have to think of the end of life of kind of construction, because otherwise you push the problem to the next generation. And why do I say it in this context? It's because particularly for compression structures, when we reintroduce these beautiful compression structures, they're also fully unreinforced. And that means that we keep all materials nicely, cleanly separated, and that gives us a very easy end-of-life strategy of direct reuse or either easy recycling, right? And so that's another kind of maybe hidden lesser known kind of quality of actually not only the geometry, right, but also separating the flow of forces. So compression, where you only have compression as in the arch, and then where you have tension, the tension tie, only there you take steel, right? So no mixing of materials. And that's already a very deliberate attitude that we follow without compromise to not jeopardize the end of the lifetime of a building, right?
What is the issues or challenges regarding the scalability of these ideas you mentioned? Because this creates a very thin shell of layer, a very thin layer of a concrete which is reinforced probably. Does this can be this scale to large buildings? Is it possible?
Thanks for asking. By the way, I have to emphasize, all our shells are unreinforced. We don't reinforce it at all. So it's a thin shell, fully unreinforced, fully unreinforced. We get the geometry right. You trust cathedrals, right? You feel safe when you walk over into Grand Central Terminal in New York City. You probably don't realize that the floors that you're walking on are being supported by unreinforced masonry vaulted shells, right? So it's the same principles. If they can stand for 500 years, our structures can stand for 500 years. So it's exactly the same idea. So how is it scalable? Well, okay. So we have done a lot of crazy things, right? So maybe you've seen the Armadillo Vault at the 2016 Venice Biennale, 399 pieces of stone held together without mortar, without glue, without reinforcement. I mean, that was crazy. It was really to show that we should perhaps reintroduce these beautiful principles of the past, right? So we have done a lot of that, but we have done all of this to now be at the point that we really understand not only all the constraints, how to really design these structures properly, but also how to engineer them safely. And not only that, how to engineer them with tools that other engineers can judge, right? So that are used in modern day practice. So we have done a lot of research in that direction. And so now we're scaling it up because we have found a very cool application for shells. And that is in our floor plates. So basically within the same structural thickness or the same package of a regular floor, we hide a super efficient structural shell that basically does these reductions that I said earlier, right? So up to 70% of concrete and up to 90% of steel. So how can we now scale it up, right? So because we have built this already, the floors in the Nest Hilo unit, for example, they are already these floors. They span 5 by 5 meters with only 3 centimeters of unreinforced low-strength concrete. So it works. It's a beautiful floor. They are in perfect condition. They look awesome and so on and so on. But they're cast on site. So that is not scalable. Can you imagine complex formwork? You need to move it from bay to bay. That doesn't work. So we have since then developed the Ripman floor system. And the Ripman floor system is a discretized version of this efficient structural form. So in a way, we are returning back to the historic principles again, right? So we're making this into large masonry blocks that we can easily assemble. And because there was so much promise, we set up the spin-off, the ETH spin-off Vaulted. And with that spin-off, we are commercializing these floors. In fact, we already have 4 projects that are committed, 2 even that are fully signed. The 2 signed are for, one is 6,500 square meters of RFS floor. So that is more than 180 floor units are being built in this project. And another one is around 5,000 square meters. So this is real.
Is there any limitations in terms of heights? Like if you go like 10 stories, 20 stories with that technique.
In fact, there's no limitation because we just replace the infill of the floor. And in fact, the higher you go, the more repetition you have. So actually, the molds for the prefabrication will become more efficient and you can optimize the cost and the sequence. But so actually, Hamid, for me, we will come back to strength through geometry, right? Because how are we able to now transfer these crazy shells into real projects? The only reason we can do this is because we found a way to sell them at the same cost as our regular reinforced concrete floor plate. So how is that possible? How can you introduce complex geometry? Of course, if you just compare the element, no way. We are always more expensive. There's no way. You cannot challenge how we have built for the last 100 years and optimized how we built these super inefficient, super high emitting kind of floors. There's no way. So how can we offer it cost neutral? How can I claim this? It is because, again, the strength through geometry. We save so much mass that this mass saving has so much savings on the columns and on the foundations that when you calculate the entire building, then you see that basically it ends up being cost neutral, that you can offset the additional cost of the floors. But by the way...
and also on... I was interested to know on what scale is it enduring to the earthquake?
The thing is, I mean, so the floors in buildings are typically being used for diaphragm action, right? So diaphragm action we also provide. So our system has a continuous layer that provides diaphragm action. And they are very stable by themselves. So the elements are very stable. But then, of course, the global lateral bracing of the building, you need to do in the traditional ways, right? So you need to, of course, still have stiff cores and things like that. But so what I'm saying is you can decouple that, right? And so for every project, we work with the engineers because now we want to be involved so that this innovation is properly introduced in the market. So we are really involved in the first projects. And then, but there's many ways to go around it. So yeah, so actually the medium high rise is perfect. This is perfect for 20, 40 stories. This is all great.
Mm-hmm. Great.
Of course, I mean, in Turkey, you have particular kind of earthquake requirements, so one has to double check and all the interactions and so on, right? But 85% of the world we can already cover. So maybe not quite yet in West California, not quite yet in Chile, in Tokyo, in Turkey, not quite yet, but in the rest of the world we're doing okay. Yes.
Yeah, we'll get there with the rest of the world as well, soon enough. I've seen your presentation in Belgium, in Ghent, actually, in 2022, and you discussed about all these ideas. That's why I was interested to know more details about it. But talking also about the Nest Hilo, which is one of the great projects that I was so excited about it, and the construction techniques with these thin layers, which creates a flexible form of concrete shell. Can you describe what other features this project had that it made it much more different than the other ones that you had before?
Okay, yeah. So basically, I already talked about the floors. So for us, the Hilo project was extremely important because it was the first time in our context. So we had done already several projects with similar ideas in South Africa, for example, in Ethiopia and so on. But it was the first project where we really could demonstrate the power, the relevance, the feasibility also of these principles in a real project in a European context, right? So that was super exciting. So actually the key point of Hilo is the floors. But of course you're referring to the expressive roof that we also built in Hilo. And there, I mean, we pushed a lot of innovation in the shell as well. But I want to, before I share my excitement about what we have done with the roof shell, is I want to say also that this project started in 2011 already, right? And so in 2011, I was not only a very young professor back then, just 2 years out of my PhD, but in 2011, only a few people were talking about sustainability, about this, and this. So actually, I just want to give this a little bit as a disclaimer, right? So in what context this project emerged. But nonetheless, what we wanted to show with the shell is that we used a flexible formwork, so a hybrid cable net fabric formwork, to realize 180 square meters of 5 centimeter concrete shell. That's how thin the first layer is of this shell. So can we realize this with a pre-stressed kind of formwork, right? And the reason that we went in this direction is because large structural shells, like for example the Rolex Center in Lausanne I often use as a beautiful large scale kind of shell, right? But that's, you build a one-off structure, a beautiful timber structure that will last only 28 days until the material, the concrete cures and you're ready to decenter. Not only that, you need a lot of formwork to support all of this wet concrete. And so we wanted to challenge that status quo. And we wanted to challenge this at a scale that matters, right? You had seen a lot of excitement about fabric formwork, very small scale things, right? A lot, very academic things. And we wanted to show that you could do this at real scale. And so we developed this system as a kit of parts. The kit of parts was used in multiple projects already, right? And so that is nice. So we had really a robust way to kind of form this concrete, to bring back the beautiful shells of Heinz Isler, of Felix Candela, but without the waste of building them, without the construction demolition waste that is needed to kind of generate them, the single-use materials in construction. And so, so that is where we started with. But then, Hamid, when you scale up an idea that looks promising in academia, it can end up being quite challenging because, of course, at such a scale, how do you control this geometry? So we already had papers that wrote we have to pre-stress it non-uniformly so that the formwork is a bit higher so that under the weight of the wet concrete you hit perfectly the geometry, right? So sounds very smart, but how do you do this in reality? In reality, you need to measure where your shell is. You need to find, because if you, for example, all the different cables, if you put turnbuckles at all these different cables, then how do you figure out which of the 90 trillion combinations of tightening and loosening, which one is it that will redirect your formwork exactly where it needs to be? So these are kind of questions that you would never think about when you're doing something at a small scale, but so tolerance control, execution, logistics on site, those are the real questions how you can scale something up. But maybe in summary, what we really showed with the Nest Hilo roof, which I'm very excited and proud about, is that it's the first project, so the entire Nest unit is the first project that uses Compas as a central data structure to generate all the information for the 40 subcontractors. And all of this innovation happened on site by real contractors, right? So this is not something that you do in your lab in a controlled environment and then you bring it and then you celebrate it. No, this was done with real practitioners. So that we're proud about. So we really managed to coordinate and to deliver a project on time, so on budget, on time, and within 4 millimeters of tolerance, which is rather crazy. Incredible. For a concrete structure. So we could do this because of Compas, kind of as a director, kind of controlling all these collaborators. And then secondly, what we really showed in this process is that our kit of parts, how we designed the node in this cable net, in the node we embedded all of the different features. So how we measured where our formwork was, that was included in the node. How the worker on site needed to figure out how thick locally the shell had to be, that was embedded in the node. Where to attach the reinforcement, that's embedded in the node. How to install the next layers was embedded in the node. So through extensive prototyping, pre-design, digital fabrication, mock-up and testing all of these conditions, we could come with a system on site where we had no more issues, no more challenges, and the global complexity was reduced to a local operation. So that basically allowed this innovation to go on site.
Incredible.
So the object by itself is cool, makes you wonder, makes you visit the Hilo, then you learn about the floors. But actually, the process, how we got there, is much more important. And that's why I wanted to talk about this maybe a bit more.
Wow,
but on the other hand, Hamid, and you need to come and visit us. If you go visit the Hilo, it's a crazy space. It's super cool. It's like a big cathedral. It has super great acoustics also because of all these different features and geometries.
Like that, yeah.
And the people that work in it, they love it, right? So I mean, the only thing that they don't love is that every week I show up there with another group of tourists coming and visit. Maybe that's less cool because it's an office building. And but except for that, it was a nice success.
Incredible, incredible. Yeah, truly, Nestilo was one of the projects that I'm following since 2015, I think. And I was incredibly excited when this structure is gonna be finished. I've just seen only in the photos. Hope I'll visit soon.
Yeah, cool.
Well, you talked about Felix Candela, and let's go with the Knit Candela project that you guys worked with ZH Code. And can you discuss a little bit about the knitting technology that you were bringing in this project?
Yeah. So actually, specifically the knitting was brought in by Mariana Popescu, who is now a professor at TU Delft. The framework of her PhD was actually large-scale flexible formworks for shells, right? And then she brought from a personal interest actually the idea of knitting, and where the idea actually came from was that because the other projects we were doing around the same time was we were realizing or developing Nest, right? And that is kind of a cut fabric. So it's with cutting patterns and seams and very traditional kind of way of bringing a fabric together. And so then the initial investigation was like, how can we actually use knitting to reduce the amounts of cuts, to be able to drape non-developable kind of geometries with a continuous kind of knit. So that was the starting point. But then increasingly, the more we kind of got familiar with this technique, and so Mariana was discovering all of the opportunities, then we saw that the knit could be used also to, for example, make sleeves where the cables can be embedded, make double-sided fabrics to create structural stiffness, to have specific openings or connections or elements that can help the workers on site to explain what they should do or where to attach the reinforcement and so on and so on. So basically, with the 3D knitting, we went one step further than the node that I was describing earlier. So now we have a continuous knit that has so many features, so many elements that basically explains the logistics on site. And so when I was having a beer with Xiaojie in, I think we were in Beijing or Shanghai, then I was sharing these kind of ideas and so on, and then he said, oh, we are opening an exhibition in 3 months from now, what about we collaborate? I'm like, whoa, sounds awesome, but 3 months from now is very short, so isn't this a bit crazy? And then we decided to go for it, and that was the starting point of Knit Candela. So and why is this a relevant starting point, by the way, is that we also with this project wanted to kind of see like what is the right level of technical innovation that is appropriate for that context. And I had worked before with Mexican laborers, and they're highly skilled. So they're highly skilled in brick vaulting. They're super skilled in concrete finishing and so on. And so we said, okay, we need to start there. So can we give them literally a more interesting fabric to do their skill, to really demonstrate what they can do? And that is actually how Knit Candela came about. So we wanted to even push the structural geometry of Felix Candela by being even more precise with our formwork. But then we did this without needing any support from below, without any kind of single-use material. And so we also left the knit stay in place so that we had a unique aesthetic on the inside. So we had the tough kind of cold concrete outside and the very kind of soft, beautiful, colorful kind of inside of the knit and so on. So we used the knit to create a sophisticated structural geometry on the inside with all the different layers and all the different features. And we did this with a formwork that was so lightweight, then so small that it could be packaged and carried in 2 suitcases in economy. So Mariana and Lex took these 2 suitcases to Mexico City. They came on site, they deployed the formwork, and directly workers with whom we never collaborated before could start working because it was so intuitive. All the intuition, all the logistics, all the pieces that were needed were basically embedded in this fabric. And that's that's for me kind of a nice that was a nice success to actually
Yeah,
do this remote collaboration in a way, right?
Yeah, incredible. And we discussed about energy efficiency with thin shell layers, and also different techniques of robotics and fabrication, digital methods. How do you see the future of digital fabrication with all these technologies? What is the vision that you have for the future of realization of the project and structural engineering?
Yeah. All right. Well, I mean, that's quite a question, but I'll try to break it down and to tackle it one by one. So for me, a key thing or a key opportunity about digital fabrication is that you can realize sophisticated or bespoke geometry, and there has been so much development and research that you can really start to challenge the status quo. So, of course, if you can place material exactly where needed, then you can significantly reduce what's needed. So for us, this is an opportunity to introduce structural geometry without a crazy additional cost, but also without necessarily a lot of waste. So, for example, when we do direct 3D printing of components, then that allows us to realize these geometries without kind of the molds associated to it and so on. So that is where I see a lot of potential, but I see a lot also, honestly, I see also a lot of danger or challenges, not danger, challenges to overcome. And that is like, while we do that, so many people have kind of focus on one performance. For example, reducing the amount of materials. Okay. But then in concrete 3D printing, if you reduce the amount of materials, but you use a super high strength concrete paste, cement paste, instead of a low strength concrete, then the impact of the material is so much higher than what you save in weight, in mass, and so on.
It doesn't make sense. Yeah.
You're kind of offsetting all the benefits, right? And so another thing, like if you, for example, large scale 3D printing, so very fascinating. You built a building in one go. Okay, great. But what I see as a challenge there is that how will you repair such a structure? How will you take it apart? So at the end of the lifetime, because you squirt your concrete, you embed your reinforcement, you spray foam your insulation and so on and so on. So basically you have a monolithic kind of thing that all becomes mixed material trash. It all goes to landfill. So what I see as a bit of a danger in all of these explorations in additive manufacturing, digital concrete and so on, is that they focus on one aspect. Or they focus, for example, on productivity, but we can build it so much faster. I'm like, yeah, well, great. But what about then the next generation? You produce waste for the next generation already. And so it's, I think we need to get to a level where we look at all the dimensions of sustainability and circularity, right? So reducing what we need, reducing waste, but also using the right materials, thinking of the end of life, right? And so there's a lot of opportunity like this in digital fabrication. We demonstrate it. With our floors, we demonstrate it. We are as low carbon as the absolutely best timber solution for a floor, right? Even that we use concrete. But we use concrete exactly how it wants to be used. But on top of that, and that is how we differentiate, we're fully circular. You can disassemble our floors as easily as you assemble them, so you can reuse them. We keep the material separated. I talked about it earlier, so you can easily recycle it, end, right? And so I think, well, no, I don't think. I am convinced and I witness that we need to, in the realm of computational methods and digital fabrication and so on, we need to get to that level. That we are not kind of, because otherwise it's almost academic, or actually in practice they do the same, right? They focus on money, they focus on a green label, they focus on this, and they forget the other aspects. And I think we need to use our knowledge, our methods, our tools to do better, not to create other problems, right? And so that's, I hope that makes sense. I mean, it's I'm a bit self-critical, I must say, of the entire field. Self-critical because I'm part of this field. We're trying to do it differently. but we have a long way to go. So, and we should not get fascinated by our tools either, right? And that's why I made the comment earlier with Nit Candela. We wanted to really see what makes sense to go on site. Surely not to send a robot that would do it for them, but to only send kind of a knit that then allowed the local craftspeople to do something unique. I think that's more exciting, and we need to do this more.
Yeah, incredible, incredible. Of course, 3D printing offers good benefits, but also has lots of challenges, and it's not easily scalable as well.
Yeah.
So
well, by the way,
we'll
Hamid,
see the future.
Yeah, yeah. Well, by the way, that is when we do 3D printing, and I'm actually not necessarily an advocate for 3D printing, but when we do 3D printing in projects that it makes sense, then we do it in a discretized way. We make components that we can assemble together, we can take them apart, we can take a component out when we need to repair it. We offer
blocks.
Yes, yeah, blocks. We're back to blocks. Yes.
Yeah,
exactly.
So, as an educator, how do you integrate your research and professional experience into teaching methods? And what do you expect from your students that take away as the final outcome of your sessions in the universities?
Maybe as a first disclaimer, I teach the very first years in architecture. So I teach the base courses in structural design. So basic structural design. So in the first semester, architecture students, the 350 architecture students, they have me as one of their professors, right? And I love that. I love teaching the basics. So it's clear that many of the aspects, the computational aspects, the shell and so on, that is not relevant in these kind of classes, or it's too advanced for the starting kind of students. That said, I hope you notice that I'm very passionate about trying to do things better. And an important aspect of doing things better is including structural constraints and also fabrication constraints from the beginning in your architectural design. We combine these things through computation, but so what I share with all of my students is kind of this awareness, this kind of attitude of not disconnecting architecture from engineering, from construction fabrication. So I think this is already almost the most important thing. It's to actually approach the architectural project in a much more open-minded, integrated kind of way. So that's maybe the first thing. Of course, I teach them also approaches and tools. So we teach them graphic statics. In fact, the tools that like Rhino Vault, historical tools that we were known for, that we also used to design the Armadillo Vault, that I used to analyze the historic structures with and so on. They are based on graphic statics. So the 2D version, the original version of the theories behind all of the methods that we use today as BRG is graphic statics, and that I teach the students. And what's amazing about graphic statics is that I give the students something super powerful. While they're designing their geometries, in graphic statics, you also are designing the forces at the same time. And so you do this not with equations that maybe could be very confusing for a designer, but you use this in a graphical technique that allows them to explore geometry and forces at the same time. So beautiful. It's actually a bit the same as the structural principles that we're trying to reintroduce. Graphic statics was the tool that all the master builders were using in the past. So you know Gustav Eiffel, right? The famous tower and beautiful bridges and so on. All these structures were built with graphic statics or designed with graphic statics. Gaudi designed this Parc Güell using graphic statics. So all these master builders used really graphic statics. And we have forgotten this technique because the computer came in, and so engineers were happy to just kind of put in a model and get a yes or no answer, but engineers lost their way how to really design, how to discover good structural form. And these techniques we teach our students, right? That said, I am excited that from fall 2025, pending approval, so there's some internal approvals, Tom and I will be leading a totally new course, which is a master's in advanced studies in computational structural design, where we will basically bring all of the historical topics of the BRG, so advanced architectural geometry, non-standard structural design, integrated computational structural design, so engineering tools and so on, really robust data structures and how to do proper computation and develop tools. We will offer all of this in this master. So let's see. Soon we will start making a little bit of noise, and I'm looking forward to not just teach the basics to architects and engineers, but also to start to kind of beyond our open source platform. That's maybe one way, and we will keep pushing Compas, but we think we have a responsibility to share how we work to more people, and so that we will do in our new masters. So looking forward to that.
Yeah, looking forward to it. So let's talk about AI. With the advancements in AI, how it's helping not just AI with all these digital tools. Actually, you mentioned about the computational tools at the beginning, but if you wanted to focus a little bit about the integration of AI in the design process, which again, at some points we had machine learning processes embedded with some of these tools. What do you think about AI and what kind of helps it can do for structural engineers?
Yeah. So I mean, I'm not generally a fan of this transition, and I think it's also clear in what I'm saying is that you start from first principles. So you really have to understand and things like that. And so what I think is maybe problematic or challenging or something to be very aware with tools like machine learning and AI is that they create a black box, right? So the input and the output is not directly correlated necessarily. And so I find this dangerous. We already came from an area where we had this kind of danger, where you could put anything in a computer and analyze it and come to a solution. And I think that is partially why we're in the mess that we are today. Because anything was possible, and you stop thinking about what makes sense for that material, what makes sense structurally, fabrication-wise, detail and things like that. So I think it's important never to forget that. But on the other hand, we use AI all the time, right? We use AI to suggest kind of design alternatives within a constrained compression framework, compression logic, for example. We use AI to program new tools where we don't have to be as precise in programming all the different variations. You can describe the problem, and so we embed AI in our tools, in our through Compas, right? And so it opens up a totally new way actually of programming very sophisticated kind of tools. And of course we use AI to browse through databases. We use AI to make sense of the crazy project that IFC is, so the format behind BIM. How can you browse through all these classes? No chance. So we use AI in many things, but I am a little bit wary for generative AI where there is not a clear connection between what you put in and what comes out, right? I think we should not lose. In fact, I am pushing, and I have been pushing for, we need to get away from too many black boxes where we don't know what's happening. We need to make our processes white box. And that is also, by the way, why we do true open source, right? Why we don't just share tools or softwares. No, we share tools that are open, where you can see how they work and so on. And I think we need to hold on to that, because otherwise we are not going to solve the big questions that we have to solve today. But AI is a great tool, helps us to optimize, productivity increase, open up design spaces and so on, but it should not replace our expertise. It will never replace our expertise. AI is not good at precise math, and physics, gravity is precise math, so we cannot replace ourselves.
Absolutely. So last two questions that I've got. What do you think about our platform PA?
Well, I mean, who doesn't know your platform? You know, so it's really great. You guys are it's impressive how fast you are on picking up all the latest and the most exciting new updates and things like that. You're always one of the first ones kind of highlighting things. So I mean, I think for many of us, it's kind of the reference to know what's going on, right? So to stay up to date with the entire world. I told you earlier before we started, I'm getting tired a little bit of talking about what we do. We want to make it happen and we are setting up these companies and so on. But obviously I couldn't refuse yours because I think you are in the selection of kind of people that you talk to. It is also becoming kind of a platform where key voices are being heard. And so, of course, I had to say yes to this invitation. And so I think those two aspects are important, kind of like hearing the influencers in our field, to hear them firsthand speak about their work is super important. And then secondly, also, awareness, right? I mean, so where do you go to know what's happening today, right? What is the new stuff out there, right? And so those two aspects, I think you're doing really well. So congrats on that.
Well, thank you so much. This is our duty and our mission to give exposure to good knowledge and pioneers and share them with the enthusiasts, and so they can follow if they're interested as well. So based on all these experiences and the innovative projects that you've been a part, and also you've been pushing beyond the boundaries, what kind of advice would you like to share with young and aspiring architects and designers?
Yes, maybe it will be a bit provocative, and people from practice might roll their eyes because they're not used to work like that. And so number one is I think outside of your box, in the sense like don't let yourself be pushed in a silo. I think with the challenges ahead, right, without having to start listing the facts on climate change and all the other crises that we have to kind of handle, this cannot be done within kind of our historically grown silos. So enrich yourself with additional knowledge, right? Don't just be an architect that only designs, right? Know something about computation, or become a hybrid engineer like me or almost everyone on my team. Then you will have the tools really to kind of start to innovate, to challenge the status quo, to do exciting things. And it's not only relevant, I believe, it also makes a much more interesting career, right? I mean, with the tool sets that we are using day to day, you're having fun. This is very different than drawing 10, 20 sketches for a star architect because they need multiple options. I mean, it's much more fun to have a broader set of skills. So that's maybe the first thing. Second thing that I want to say is that really educate yourself, and not just kind of in a naive way, wood is good, concrete is bad kind of level of sustainability, but really study sustainability, study opportunities for circular construction. And really you have to be, as a future architect, future designer, future engineer, you will have to be a total expert in sustainability. You will have to. We have to take action, we have to be responsible, we have to take our responsibility, and that can only happen when you really know what you're talking about, right? And so that I notice, we have a lot of work to do, so educate yourself, you will stand out, you will not be relevant if you don't, so really do it. And then maybe lastly is challenge the norms, challenge the habits, challenge the regulations, really. In everything that we do, nothing fits perfectly in the norms, in the codes and so on. But that doesn't mean that we don't build according to the regulations and so on. It just means that we challenge where things come from, right? So and this is so needed, this attitude is so needed to change things, right? So many people are hiding behind, yeah, but that is not how it's done. No, but that is what the code says and so on. And so you have to keep challenging all of these outdated, conservative kind of things, because we need to act, we need to do better, and that will not happen by following the letter of the code. We will not get there. We need to change things. And so everything that we have done by breaking, changing, bending, interpreting the rules, right? So we have not followed the rules ever. And that doesn't mean that we're dangerous. It means that we basically do the extra effort to make things change, to make a change, to do things better, right? So I think those three things, yeah.
Well, thank you so much, Philippe. This was really amazing conversation, very insightful, and also the tools that you guys are developing, it's very great. And I remember I looked into Compas when you published it a couple of years ago.
Yeah, a lot happened.
Yes, yes. But I think regarding to making some noise, it was not that much. That's why I forgot it. But I'm sure everything that you guys are doing is incredible. And looking forward for the future tech or projects that you guys are working on. Looking forward to meet you in person. Thank you so much.
Sounds good. Thanks, Hamid. Thanks for this talk.
Thank you so much and take care. Bye. Guys, thank you so much for watching the episode. I hope you enjoyed it a lot. Again, I want to spotlight Pacademy, an online architectural educational platform that spreads the idea of using parametric design, computational tools, and artificial intelligence in architecture. You can register and join the live workshops or watch the previous studio workshops recordings. Don't forget to subscribe and hit the bell notification so you don't miss any new uploads. Thank you so much for watching the episode. Hope to see you soon in the future episodes.